So we've finally developed the Turing model in fullness to the extent that I want to. And by doing that, I want to kind of remind ourselves of what we've done. What we've done is we've formalized / mechanized / standardized this idea, this picture, this general kind of schema for how human pen and paper computation works. And it should, and through doing this example of addition, what I wanted to show you is essentially how natural it is to just go from any pen and paper computation that you're used to a Turing machine which does it for you. Because the Turing machine which does it for you is more or less just an explanation of how that works. And so it's very natural to assume something that historically was extremely controversial until Turing came along. And so that has to do with the Church-Turing Thesis. So I'm going to jump to a PowerPoint now and open this up. How do I start a PowerPoint? Okay. This is the Church-Turing Thesis, and the Church-Turing Thesis is essentially something that we should have that we hopefully have convinced ourselves of as we did the process of developing our model in the first place, which is the following right here. Any mechanical human pen and paper computation can be represented with the Turing model. That's, I mean, in terms of what we've been talking about, this really just boils down to the claim the thing we've been doing wasn't a failure. The whole point was to do this, right? However, a claim like this can't be proven mathematically because it's fundamentally linked to material physical reality in a way that we're going to talk about. Because, I mean, just look at the statement. Mechanical, physical, human pen and paper computation, a thing happening in real life, can be represented within the Turing model. This is not a mathematical claim. This is not a mathematical claim, and so it can't be proven mathematically. It's just something that you have to either accept or reject. And the funny thing is that almost all mathematicians accept this, and computer scientists. And that's really odd because mathematicians do not generally accept much of anything. They don't accept the axiom. There's tons of mathematicians that reject infinity as a concept. You know, I mean, you can find all sorts of crazy people, but this one is pretty uncontroversial. And so in order to understand why it's uncontroversial, I think that it's in order to look through the history of it, because I think that's also going to set the stage for the connection between computability theory and metamathematics that we're going to eventually bridge into. So the history of computability and also the history of Gödel's incompleteness theorem, they start at the exact same place at the exact same time. They both begin, the stories have the same beginning point, and that beginning point is the International Congress of Mathematicians that happened in Paris in the year 1900. And that is a very pivotal moment in mathematical history because this guy, David Hilbert, a very famous mathematician at the time, posed a list of problems that were meant to be kind of the great questions that mathematicians should agree that we're going to prioritize as like a little intellectual community. These are the things that we're going to pursue as for answers to in the 20th century. It was the millennium questions, I think, or whatever. And of these, the second and the 10th are of interest to us. The second is not of interest to us just yet. We're going to come back to it later. And I'm going to be skipping over a good chunk of the history to focus on computability for now. The 10th is the following, and it's not this problem up here. And by the way, this problem, this is a German word. I'm not going to try to read it. I refuse. It means decision problem. This word that starts with an E that I'm not even going to bother trying with translates in English to decision problem, and so I'm just going to call it the decision problem. Although that's not the 10th problem of Hilbert's list. The 10th problem is this. Determination of the solvability of the Diophantine equation. You don't need to know what the Diophantine equation is. I barely know. Given a Diophantine equation with any number of unknown quantities and with rational integer coefficients, to devise a process according to which it can be determined in a finite number of operations whether the equation is solvable in rational integers. Now, you don't need to process much of that. The significance of the problem to us is to note what it's asking for, which for the time was a sort of novel thing to ask for. It wasn't asking for a yes or no answer. It wasn't asking for a theorem to be proven true or false. It's asking for an algorithm. It's asking for a process. It's asking for a general effective procedure for determining in a finite number of operations whether whether an equation is solvable or not with rational integers. So that was significant for that reason. So first of all, we should note that the word computability is not really being used yet. In fact, the word algorithm is just about to be coined to refer to these kinds of questions. Right now, what people are typically using as vocabulary, and I think this is still useful vocabulary in some instances, is that they're talking about effective procedures. So the existence of an effective procedure is kind of what we're talking about instead of computability, even though it's going to turn into that. So people started to get interested in this, and at the same time, it was also becoming the kind of fashionable thing to do was to explore formal kind of toy proof systems at this time. People were starting to get very meta about their mathematics. And so these two kinds of things going on at the same time, this interest in algorithms and this interest in formal proof systems sort of came together with a much more interesting claim, which is the actual decision problem, which is the following in bold here. Does there exist an effective procedure for proving mathematical claims generally? In other words, can the process of doing mathematics, can the process of being a mathematician be automated? Not just like an individual mathematician, but like, can mathematics just be automated by a single, I don't know, big computer? That's kind of what we're asking here. It's a very bold question. But it's also vague. It's vague from the standpoint of mathematics. It's an interesting claim, but there's a lot to do just to even state it in a way that's approachable mathematically. And so, in particular, we need to do two things, or there needed to be done two things. So, one, what was needed was a mathematical notion of the concept of effective procedure, i.e. a mathematical definition of what it means to be computable. So, we have this effective procedure word here. What does that mean? And then two, you need an actual formal system that's the good one, a formal system of logic like a mathematical theory of mathematical theories, a meta-mathematics of axioms and formal proof systems. So that was being explored at the time, and people were starting to develop ideas like first-order logic in general, observing their own behavior, right? But that was starting to come about. And so this is really the birthing of these two fields simultaneously. It's noteworthy and very telling, I think, that these two things arose simultaneously, which is why I'm giving a talk on both of them at once. Computability and meta-mathematics are linked at the hip in their inception, from their birth. So let's get into the the focus obviously for us is going to be this first thing here. This is the beginning of mathematicians starting to try to formalize this idea of an effective procedure. And so that really begins with these two guys, Church and his student, Kleene. And they started out with the early 30s with defining this notion of what they called lambda definable functions. And they proposed that a function be considered computable or effectively calculable if it was lambda definable. This is the lambda calculus that some computer scientists tend to learn about. Gödel, who you might have heard of, strongly disagrees with this. He calls it thoroughly unsatisfactory. According to Kleene, his only idea at the time was that it might be possible, in terms of effective calculability as an undefined notion, to state a set of axioms which would embody the generally accepted properties of this notion and to do something on that basis. So Gödel didn't like the idea of defining a set of functions as the kind of base definition of computability. He had a problem with that sort of philosophically, and that's justified. It didn't see, what does that really tell you? If you're defining computability via a bunch of functions, you haven't really said what computability theory is. You've just said, here's the computable stuff. So Gödel doesn't like that, and Gödel's interested in maybe we can define computability in terms of like a set of axioms. Maybe that would be better. Axioms, by the way, are base statements that you just assume are true, that you take as givens in order to kind of build a theory. So the problem was that at the moment when he said this, at least, Gödel didn't have actually much to offer in as an alternative. He liked the idea of axioms, but he couldn't come up with any. In fact, what he came up with was the exact thing that he doesn't like. He came up with his own model of computation defined in terms of a bunch of functions, the recursive functions. And this is the beginning of that word being used, by the way, recursive. Actually, that's not true. It was used earlier with Peano arithmetic and stuff, actually. But anyway, he proposed the same thing, essentially. He didn't like the idea of doing this, but he did it anyway. He proposed that a function be considered effectively calculable if it was recursive. So they quickly proved that they had actually defined the exact same set of functions. The Lambda definable functions and Gödel's recursive functions, they immediately figured out were the same set of functions. They were just defined in two different ways. They were, in fact, the same definition of computability, though still, at this point, nobody's calling it that. So, moving on, here's Gödel, by the way. This is a picture of him. This is a picture of Post, who is going to be coming in with some spicy takes here quickly. So by this point, you've got these two motions of computation. Nobody's really sure what to use. Nobody's really satisfied with either one of them. But let's check in with the boys working in the second department on the meta-mathematics. They are making good progress. And they're coming up with some cool proof systems that everybody likes. Building on this, Church was able to use his lambda definable functions and also Gödel's theory of the recursive functions. He needed both, I think, to prove the decision problem in the negative, based on his definition of computation. So this wasn't entirely satisfying to people at the time. In comes Post, and Post comes in with a hot takes, and he basically says, you guys are all wrong. He says he rejects this idea that the lambda definable and the recursive functions constitute a proper identification with computability. And he also rejected the idea that computability should be axiomatized, which is what Gödel wanted. So let's quote him directly, because he's got some subtle takes here. Actually, the work already done by Church and the others carries this identification considerably beyond the working hypothesis stage. But to mask this identification under a definition blinds us to the need of its continual verification. So that's a little hard to parse, but what Post is observing here is what we've observed already before we started to get into this history, that he's trying his best to kind of become a materialist and realize there's a bit of a problem with trying to jack computability as a concept completely away from material reality and into the realm of mathematics, because he's basically saying here, but to mask this identification under a definition blinds us to the need of its continual verification. What he's saying there is that the only way to really be happy with this definition of computation is to just repeatedly prove with every new problem that it is lambda definable or that it is recursive. That's the only way to do it, and that's a bit odd. And so yeah, he's pointing out that everybody is resigned without admission to being content merely confirming over and over again that this or that effective procedure was one of the functions considered computable. According to Post, there's no intuition or understanding to be gained from this, and the axioms won't help. So Post is not satisfied with any of this stuff. And then, here comes our boy. So in 1937, based on talk from 1936, so sometimes it's said that the paper is from 1936, and sometimes not, doesn't matter. Turing steps in with his paper on computable numbers with an application to the decision problem, in which he defines his Turing machines. He calls them A machines in there, but they are the Turing machines that we just talked about. And he goes on to prove his version of the decision problem false. And he also proves that his model is, once again, equivalent to the other two. The Turing model is equivalent to the lambda calculus model, is equivalent to the recursive function model. They all just keep turning out the same. And so the question once again becomes a twofold thing. One, is this definition of computable all-encompassing enough, which it seems like it is because you keep getting the same set. And then two, if they're all just good enough, which one's the best? Everybody was very intrigued by the Turing model when it first came out. There's an interesting quote from Wikipedia here. Church was quick to recognize how compelling Turing's analysis was. In his review of Turing's paper, he made clear that Turing's notion made the identification with effectiveness in the ordinary, i.e. not explicitly defined sense, evident immediately. We should be very familiar with that feeling. Church is basically, what this is saying is that Church actually read Turing's paper and felt the exact same way we did, that there's something very natural or even self-evident of the Turing model as computation, or at least pen and paper computation. So by showing you the development of the Turing model first, I hope that I've actually kind of emulated this feeling for you that Church is feeling upon reading Turing's original paper. The Turing model feels natural. It's rooted in reality because it's based on it's specifically based on human computation. We're not defining some weird set of operations that define functions mathematically. We're starting with this idea of pen and paper, and we're going from there. And so that's why the Turing model is the most natural feeling. But it also lent a lot of credence to all the models that existed already. If the Turing model is equivalent to these guys, and these guys are already kind of, you know, two other attempts to define computability, then this is we're getting more and more credence lent at least to the fact that this is the correct set of computable functions, right? So everybody just kind of gives up eventually. We have three definitions of computability. All of them are the same. All three authors are claiming that theirs is the best one. And then this guy named Rosser, who I really can't find much information on, has a famous quote that I've seen so many times. All three definitions are equivalent, so it does not matter which one is used. So this is everybody just being like, okay, you know, fine. Everybody knew he was right. In 1943, Kleene proposed formally what would become known as the Church-Turing Thesis. I don't really know why it's called the Church-Turing Thesis. I don't know where, you know, why Gödel isn't there or why Kleene isn't there, whatever. But every effectively calculable function is general recursive. That was the original way that it was stated. Essentially, what he's basically saying there is, if it's computable, then it's recursive. And we already know that if it's recursive, then it's computable. So this thesis really is saying that we can take as a definition of computability the recursive functions if we want. But since this recursive model is equivalent to the Turing model, the thesis is equivalent to the more modern-sounding statement. I think this is the way to say it in the kind of more modern sense. If it's a computable function, then there's a Turing machine which computes it. If it's a computable function, then there's a Turing machine for it. That's the Church-Turing Thesis. That's one of the ways you can say the Church-Turing Thesis. The thesis is actually equivalent to the claim. This is a claim. But the thesis is that we should take any of these notions as the definition of what it means to be computable and get on with it. In other words, the model does not matter. So there's some equivalent ways to say the Church-Turing Thesis to what we just said. The Church-Turing Thesis, the way Kleene says it, is Kleene is basically saying that if it's computable, then there's a Turing machine. But if that's the case, then a lot of other things are true that are equivalent to that. For example, any sufficiently powerful model of computation is equivalent to the Turing model. In other words, if you can show that your model of computation is just as powerful as the Turing model, and all sufficiently powerful models of computation define the same set of computable things, then they're all equivalent to the Turing model. They can all be pointed back to the Turing model. And this is where you get this notion of Turing Completeness, which you've probably heard if you're a CS major. Turing Completeness is to show, oh yeah, it's just as good as a Turing machine, so it is a Turing machine, essentially. All models of computation as powerful as the Turing model are equivalent. We just kind of said that. If there's an algorithm, okay, this is the big one. If there's an algorithm for it, then it's computable, right? Because if there's an algorithm for it, then what we've really said, when we say that there is an algorithm for it, we're saying that there exists a model of computation in which I can describe an effective procedure for doing this thing. And so if that's the case, then it's computable because I just said model of computation. Therefore, there's Turing machines, therefore computable. So now we're getting really general. This is the part where things start to get weird. Because now we are back where we started. What we said before, the Church-Turing Thesis as I originally stated it. Any mechanical human pen and paper computation can be represented within the Turing machine model. Because if I can describe what to do with a pen and paper via like an effective computation, then I've implicitly specified a model of computation, and so it can be represented in the Turing model. Because all models are equivalent, the model does not matter, meaning that there exists a Turing machine, so the model does matter. Don't worry about it. So this settles it. This kind of settles the concept of computability as far as mathematics is concerned. There is no doubting anymore that we have the correct set of computable functions. And we've all accepted to some extent that there is no way to yank the concept of computability, completely sever it from physical reality. You just can't do it. So we are back at the original question, philosophically. What the hell is computation? We've defined it 3 times and we still don't know. But In the next video, we're going to discuss that. We're closer to the answer than we think. In fact, we might have said the answer from the beginning. So tune in for that.